Richard Feynman famously categorized the fine structure constant, 1 over 137, as the most profound unsolved mystery in physics. He challenged all physicists to grapple with why nature chose this specific, dimensionless number to define the strength of electromagnetism. Arnold Sommerfeld first introduced the constant in 1916. For a century, the Standard Model has treated this value as an arbitrary coupling parameter, an empirical constant that must be measured in a lab rather than derived from first principles. A new mathematical proof treats the fine structure constant as an exact topological necessity. In this framework, the value is forced by the internal constraints of geometry. Proving that alpha is a theorem requires us to abandon empirical physical laws and begin in an absolute void, building exclusively from the constraints of pure kinematic motion. We begin with the minimal possible rigid body. In this two-dimensional plane, three non-collinear points of equal mass rotate around a stationary central pivot in a co-moving frame. To maintain a rigid structure, these points preserve an exact phase offset of 120 degrees. This gap mathematically forces the three velocity vectors to sum to exactly 0, satisfying the kinematic requirement that the centroid remains stationary. This system possesses C3 symmetry. C3 is a group of rotational symmetries where an object is invariant under rotations of 120 degrees. Here, it functions as the strict temporal signature of the rotating points. From the solitary geometric axiom, the rotation of 3 points, every fundamental constant of the universe's coupling structure emerges through forced logical steps. The inertia tensor describes mass distribution. Here, the perpendicular axis theorem proves the axial inertia is exactly twice the in-plane inertia, a 2-to-1 ratio. This triggers the Euler wobble, a free precession without external torque. The triangle tilts, tracing a three-dimensional precession cone. Poinsot's theorem states that this torque-free motion can be visualized as a rolling ellipsoid. In generic three-dimensional space, this precession is mathematically irrational and never perfectly repeats its path, leading to the closure problem. To achieve geometric closure across arbitrary axes, the system lifts to the icosahedral group, 60 rotational symmetries of a regular icosahedron capable of trapping the wobble. This closure forces the golden ratio, phi, into the coordinates, ensuring the most uniform possible rotational distribution. The simple flat rotation has constructed a 60-element three-dimensional geometric cage, defining the environment for an observer to enter. We now embed a spin 1/2 quantum observer inside the volume swept by this rotation. Spin 1/2 is an intrinsic property of fermions, where a quantum state requires 2 full rotations to return to its original phase. This periodicity is unique. A 360-degree rotation yields a phase of -1. To return to the starting state, the observer must complete a full 720-degree cycle. Standard rotation space cannot represent this 720-degree rule. This forces a topological lift to the double cover, SU2, the universal cover of three-dimensional rotations. This lift generates the Binary Icosahedral Group. Because it is a double cover of the 60-element icosahedral group, it has an order of exactly 120. We visualize the structure through its Cayley graph, representing the group's elements as nodes and operations as edges. The spectral weight splits precisely in half, with 60 nodes forming a bosonic sector and 60 nodes forming a spinor sector. Placing a quantum observer into the system forces the geometry to double its complexity, revealing an entirely new sector of rotational space. An observer restricted to a bosonic background field, like the electromagnetic vacuum, suffers from Sign-Irrep blindness. Here, the observer cannot distinguish between a quantum state and its negative phase flip. This occurs because their measurement tools are quadratic in the wave function. By measuring intensity or energy, the absolute square of the field, the information contained in the sign of the state is lost. This blindness has a total geometric consequence. The entire spinor sector of the group dims into blackness, rendered unobservable to anyone measuring through a bosonic field. Interaction now only physically propagates through the surviving bosonic subgraph. The observer is trapped in half the rotational space. The nature of the measurement tools constricts a topological cage, barring the observer from accessing exactly half of the universe's representation weight. The final task is to calculate the exact fraction of rotational coupling symmetry that remains accessible to this sign-blind observer. We calculate the graph's spectral gap using a Laplacian matrix. The final assembly multiplies the half-accessible volume by the icosahedral gap and nutation factor. This calculation, 1/2 times 1 over 5 squared times 1 over pi divided by 1.5, resolves exactly to 1 over 137. This derivation relies on no adjusted parameters or assumed physical forces. The result is a pure geometric theorem emerging from the rotation of 3 points. 1 over 137 is the exact topological measure of the rotational symmetry available to a spin 1/2 observer embedded in a bosonic vacuum. It defines the narrow window through which we are permitted to view the universe's rotation.